Hello, everyone. My name is Yonglan Zhou. I'm a professor from the University of Copenhagen. I'm going to present our work on ByteSeries. It's a joint work with my colleagues from Hwa Chong University of Science and Technology, National University of Singapore, and ByteDance. The advent of large-scale online services has prompted the need to build large-scale monitoring systems to monitor the large number of servers, the different components in the system, and also the tasks running in the system. Time series database is a critical component in such a monitoring system. It's responsible for collecting and storing massive time series data and to serve queries for monitoring purposes. Despite there is already a large number of systems being developed for this purpose, we identify several challenges in ByteDance monitoring system that have not been met by existing time series database systems. This is the overview of the architecture of ByteDance monitoring system. A number of data collectors running on the different servers collect time series data and fed them into Kafka, and the data are then fed into the storage system in ByteDance monitoring system. There are two storage systems. One is for short-term storage, which store the most recent time series data. Another one is long-term storage for historical data analysis. The query server retrieves data from the two storage data according to the needs of the queries and produce results for the monitoring applications. So we are focusing on the short-term storage. The name of the system, the name of the existing system in ByteDance monitoring system is SDC. It's a in-memory time series database. It stores and manages the most recent data in memory. Typically, the latest 2 hours of data are stored in TSDC. It compresses the time series data in a similar way as the Gorilla system, and it provides querying interface. We make several observations that actually indicate that the requirements of ByteDance monitoring system, which cannot be met by many existing time series database systems. The first observation that we can make is that the metadata in the time series data in ByteDance takes over 80% of the memory, which is like 4 times higher than the data points themselves. So what's the metadata? So typically in a monitoring system, a time series, it can be uniquely identified by a series key. So the series key consists of a metric name, for example, memory usage, CPU usage, and also a list of tags in the form of key value pairs. For example, the location of the host and the operating system of the host, etc. The second observation that we can make from the production workload in ByteDance is that the number of dimensions has been increasing very quickly in recent years. The speed actually higher than the growth speed of the time series data points. Furthermore, many new dimensions are generated every day. This is caused by the dynamic allocation of containers and the movement of microservices between containers and etc. So every time we allocate a new container or start a new short-term tasks, a new dimension will be generated. So this is a The second observation. The third observation is that most queries in TSDC is a multidimensional query. So by multidimension, we meant that in the query condition, there is a selection on the text that it does not only involve one single dimension. For example, a query may query the average memory usage of all the machines in Wuhan, which means that the query condition contains the key value pair location equals to Wuhan. There could be a large number of dimensions that fulfill the condition. So in summary, all these observations require that we should have a effective compressed storage of metadata that can compress the size of metadata. And at the same time, it should support dynamic creations of dimensions and efficiently index the time series keys so that we can we can answer multidimensional queries efficiently. And at the same time, of course, we should not sacrifice the throughput of data injection. So in order to meet these needs, we designed ByteSeries. It mainly contains two components. The first component is memory layout. The memory layout of ByteSeries consists of an active buffer and a static buffer. And also a data conversion schedulers to convert data from one buffer to another buffer. So we designed the data structure in different buffers in order to meet the needs that we just mentioned. The memory layout in the active buffer is designed for high ingestion throughputs. It uses dynamic data structures. For example, we use a hash table. The key of the hash table is the time series key. So every time a data point comes, it will just look up the hash table and store and append the data points to the array attached to the time series key. And in order to support parallel data conversion, the active buffer are sharded into multiple active segments. We also put a size constraint on the active buffer in order to limit the memory usage of the active buffer, because the active buffer does not do any data compression. And the second buffer in the ByteSeries memory layout is static buffer. The static buffer is designed for high compression ratio. It's at the same time, it's designed to achieve high query performance. In order to support multidimensional query, we use a trie as an index structure and also an inverted index to point to the data points, the offsets of the data points in the data array. So every time a data point arrives, the data would be inserted into the data point storage, and the inverted index will be updated according to the time series key. So in the static buffer, we actually maintain two types of segments. One is the static segment, which is which does not do any data compression on the data points. So in this in the static buffer, data points are appended to the data array. Okay, so therefore for each data point, a pointer will be added to the inverted index, so that the offsets are stored in the inverted index. However, in order to compress the data points, we do not do a compression for each static segment. Instead, we do a batch compression in order to maintain the high ingestion throughput. So several static segments will be merged and then compressed in a batch manner into a compressed segment. In the compressed segment, the data points from the same dimension will be stored consecutively and also compressed using the Gorilla algorithm. In this way, one pointer per dimension is stored in the inverted index. We call the compressed list. So just to show how this data structure it looks like and how it is used for query processing. So in order to process a query in compressed segment, for example, in this query, it looks for the memory usage of the host with a location in Wuhan and ID equals to 1, and a group by the time for 5 minutes. So in this way, the first step will be looking into try and find the offsets of dimensions having the key value local equal to Wuhan and ID equals to 1, and do an intersection and to find all the dimensions that fulfill both conditions. So for example, here in the inverted index array, so the 0 dimension would fulfill the condition. And then we can retrieve the data according to the offset store here and retrieve the data points in the dimensions and do aggregation and group by. And in order to maintain high throughput data injection, data conversion scheduler will control how the data conversion between different data segments are carried out. So basically there are three data conversion processors: compactor, compacting the data in the active segment to the static segment, merging the static segments, and also compressor, compress the static segment, the merged static segment to compressed segment. So the data conversion would just check this. For example, whenever the size of the active buffer exceeds the threshold, it will call the compactor to schedule the compactor to compact the data in the active segments. So we implemented ByteSeries with using C++ and run our experiments on a 2-node cluster. And we run the experiment using a benchmark, the time series benchmark suite, and the ByteDance production workload. The first experiment shows that the memory usage of different data structure that we use, the active segment, static segment, and compressed segments. So it shows that the static segment and compressed segment can significantly reduce the data size by doing metadata compression and compressing the data points. We also can show that by doing batch-based compression of static segment to compressed segment, we can achieve similar throughput as the injection of data injection in active segments. So which means that our compression does not sacrifice a lot on data injection rates. And the memory usage of our system is much smaller than the other existing time series databases that we compare with. And we also compare our system's ingestion throughput with the other systems. So our ByteSeries ingestion throughput is lower than Gorilla because Gorilla doesn't do any indexing and compression of metadata. But ByteSeries is much higher than Prometheus and TSDC. We also does experiment on query latency, which shows that ByteSeries, it has a lower query latency than TSDC and Prometheus. Furthermore, we does a experiment using the production workload from ByteDance. The first experiment is query latency, so which shows that we run tens of thousands of queries from the production workload and run on our system. And we can see that almost all the queries can be executed within 10 milliseconds. And also 80% of the queries can be executed below 2 milliseconds. Furthermore, in terms of memory footprint, we measure the memory footprint on each node instance. It shows that ByteSeries has much lower memory footprint than ByteDance's original TSDC. So because of its compression on the metadata. Now the ByteSeries already being used in the production system in ByteDance. In conclusion, the dynamic and high dimensional time series data calls for new techniques to compress and index metadata, which has not been addressed by existing system sufficiently. And ByteSeries adopts the compressed inverted index data structure, which can store metadata in a compressed form and process multidimensional group-by query efficiently. The data conversion scheduler is able to efficiently convert the data without sacrificing the data ingestion throughput, as shown in our experiments. Thank you for your attention.